All right, my friends, here we go. So last time were just sort of going on a blisteringly fast review of all the carbon-carbon bond forming reactions we've ever done. And these are really important in building up the structures of complicated molecules. And one of the things we noticed toward the end of the discussion is we got a lot of ways of making bonds between sp3 hybridized carbons, and even some ways of making bonds between an sp3 hybridized carbon and an sp2 hybridized carbon. But when it comes to making bonds between sp2 carbons, we're somewhat limited. What we've got so far is the Wittig reaction, but in this case we're making both sigma and pi bonds, and then I suppose you could count the aldol as potentially making both sigma and pi bonds between sp2 carbons. But other than that, we don't have a lot of tools yet. And so we were considering a couple of different molecules. What if we wanted to make a bond between benzene rings? We haven't got a technique that'll do this yet, in part because you could imagine, well, why can't I just do a Friedel-Crafts? And the answer is that if you do a Friedel-Crafts alkylation, you need an alkyl halide on one side and you've got to make a carbocation. And we've never, ever, ever been okay with this as an intermediate, like ever, right? So we need some new techniques, and this is going to involve a lot of new chemistry that you may not be used to. Let me give you some examples of some reactions that we're going to talk about. These are called cuprate coupling reactions. It turns out you can take an alkyl halide and diphenyl cuprate, and you can make a new bond right there between sp2 and an sp3 hybridized carbon. Okay, big deal. We could have done that via Friedel-Crafts, except I will tell you that we glossed over this in the text, but your text says that you can get rearrangements with the Friedel-Crafts reaction even for primary alkyl halides. And so this might be a great method to get this molecule without any potential byproducts. And as you look at it, you know, we've used cuprates as basically thought about them as equivalents of carbanions before. And so it would be reasonable to propose a mechanism where these the cuprate would basically deliver the phenyl anion to the carbon bromine sigma star, and you do an SN2 reaction. But there's evidence that that's not what's going on here. So you can do the same reaction if instead you start with the phenyl halide and then react it with the 4-carbon cuprate. That will go to this molecule as well. And there, even if you wanted to think of the cuprate as being basically a butyl anion, you don't do SN2 at sp2 hybridized carbon halide bonds. So mechanism here really can't be SN2, even though chemically this works just fine. So something else has to be going on here. You can also, in this reaction, well, through a slight change in the molecules that we're using, we can also make a new bond here between two sp2 hybridized carbons. And again, the mechanism really can't be SN2 because we don't do SN2 at sp2 hybridized carbons. So this likely involves another kind of mechanism, and so we're going to talk about that. But before we do, we need to learn a few things about transition metals, and this is way outside my area of expertise, so we're sort of learning this together. Go ahead.
Do you mind scooting back a little bit? I don't think we went as far as the other class.
Okay.
So I'm kind of, the only reaction I have is to that last ketone. I don't know if
Okay. Yeah. Okay. Okay, well, sure, we can talk through them, that's fine. You're just trying to prevent me from getting to the transition metals, which is a good, I can understand that. I don't really want to go there either, but we're going to. Okay, examples of carbon-carbon bond-forming reactions. In synthesis, it's useful to categorize carbon-carbon bond-forming reactions according to what kinds of bonds they make. For example, addition of a lithium reagent, organolithium reagent to an aldehyde makes a new carbon-carbon bond here, a bond between sp3 carbons. That's a nucleophilic addition reaction. If we start instead with an ester, we can do a similar reaction. First, it's an nucleophilic acyl substitution to generate a ketone, followed by nucleophilic addition. But again, you're making sp3 bonds between sp3 carbons. This reaction, you'll remember, was a cuprate adding to the beta carbon of an alpha-beta unsaturated carbonyl compound, but the result is another bond between sp3 carbons. So right away, we've got a number of tools for making bonds between sp3 carbons. We added another in the chapter on enolates. So if you make the enolate using LDA, you get the less substituted enolate, and then you can do enolate alkylation, which is just an SN2 reaction with the enolate acting as a nucleophile. You can do the aldol reaction where we make an enolate and then it reacts with itself to give this beta hydroxycarbonyl compound, which can dehydrate and give the alpha-beta unsaturated carbonyl compound. Depending on which product is the aldol product, you either make a bond between sp3 carbons or you make both sigma and pi bonds between sp2 carbons. The Claisen reaction is really similar, only this time you get a beta keto ester and it's a bond between an sp3 and an sp2 carbon. And then we've done the Michael reaction where we had an enolate add to the beta carbon of the alpha-beta unsaturated carbonyl compound to get this diketone. Early on from 351, you did SN2 with an acetylide anion attacking the sigma star of a carbon halide bond to make a new carbon-carbon bond. This time it's between an sp carbon and an sp3. Let's see, cuprate addition to alkyl chlorides gave us the ketone. So that's an sp2 to sp3 bond. The Wittig was an unusual reaction that we didn't spend a lot of time on, but as you may recall, it clicks together an aldehyde with an ylide reagent to make a new carbon-carbon sigma bond and a pi bond. Basically, we break both of those bonds and then stitch both parts on either side together. And this is a bond between sp2 carbons, but you're making both sigma and pi. And then let's see, the Friedel-Crafts reactions, which we talked about several chapters ago with the benzene ring, electrophilic aromatic substitution. Another one, I guess this is an old favorite. Did you guys do this in 351? See, I can't remember because it used to be in 352, so I'm kind of messed up. But Diels-Alder reaction is you make two new sp3 bonds at the same time, and you build up a six-membered ring, and that's an additional level of complexity that's been used a lot to generate complicated molecules in organic chemistry. So I think that's most of the carbon-carbon bond-forming reactions we've done that are in our toolbox, but the idea is that we still don't have a lot of good ways to make bonds between sp2 carbons, especially those involving benzene rings, aryl carbons, or those that are participating already in a double bond, vinyl carbons. Okay. So what I was showing you is new reactions that work to give you some of these bonds, but the mechanisms you can't think of as happening in the same way that we've done before, because they work even though SN2 shouldn't be possible. All right. Okay, so a couple of things as we start to learn about the chemistry of transition metals. All right. First is the idea. First, you need to learn sort of how many valence electrons typically come with the each specific transition metal. We won't do them all, but we'll do some of them. By the way, if you have a tough time remembering transition elements, there's a fun little game app that you can use. It's called Atomus. I don't know if you've seen this one. You fuse atoms together and you increase them one by one, and so it's helped me remember it's scandium and titanium and vanadium and chromium and all that stuff. Anyway, it's a lot of, it's not that fun unless you're a nerd. So let's talk about the first row of transition metals. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay? Oh, I was looking at my notes though, so don't clap. Okay. These are in the row of the periodic table where we now have access to d orbitals. So we're going to have more than 8 valence electrons. Starting with scandium, it's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then if you continue on past zinc, the remaining atoms within that row, you can have up to 18 electrons. And notice that what this means is sometimes people will talk about a difference between early transition metals and late transition metals. The early transition metals tend to be electron poor. The late transition metals tend to be electron rich. And so you'll see often that the early transition metals will act pretty much as Lewis acids, and that'll be it, whereas the later transition metals will have more rich chemistry. Some other transition metals that are useful to know: molybdenum comes in the same column as chromium. Ruthenium is below iron. Rhodium is below cobalt. Palladium is below nickel. And then some other things you might hear about: osmium, iridium, and platinum. I don't remember, but did you guys learn in 351 about the sharpless asymmetric epoxidation-ish? Yeah, that involved titanium. And you also learned about osmium tetroxide dihydroxylation, right? Osmium's one of these transition metals. Okay. Well, so you're going to have to get used to this, but it's the same kind of thing as, okay, carbon has 4 valence electrons, nitrogen has 5, and so on. Now, the types of transition metals that we're going to be dealing with are sort of called organometallic complexes because you have the metal sort of at the center, and then it's often surrounded by ligands. So one such complex is tetrakis triphenylphosphine palladium. And one of the things you're going to have to get used to in thinking about organometallic complexes is that we're going to be somewhat sloppy about lines and formal charges on atoms. Rule number one, though, is if the complex has a charge, we must show the overall charge. All right, so by the fact that I've not shown you a charge, this is a neutral Palladium complex. There are a couple of different types of ligands that can participate in complexes with transition metals. The other thing is we generally will not draw lone pairs on the metal because in many cases there's too many. Whoops, I drew the exact same thing. Okay. So I'm going to show you what's called a ligand dissociation reaction. The metal is the center, and then these groups attached to the metal are called ligands. And that just means they bind to the metal. There are two different kinds of ligands. If we do a ligand dissociation reaction, with triphenylphosphine as a ligand, I'm sorry, what the heck is going on there? Palladium, good. Triphenylphosphine is just a phosphorus with 3 benzene rings on it. Phosphorus is from the same column of the periodic table as nitrogen. So this is a phosphine, analogous to an amine. Phosphine leaves. The ligand that leaves is neutral, and the complex that's left behind is also neutral. Okay? This is called an L-type ligand. And these are typically, L-type ligands are typically molecules that have either lone pairs or pi bonds that we're going to say coordinate the metal. But we're going to count those lone pairs as part of the ligand. In other words, these electrons came with the phosphine when it bound the palladium, and they're leaving with the phosphine when they're binding the palladium. In contrast, if you use bromine, bromine will leave as negatively charged bromide, which means the complex has to be positively charged. So in the ligand dissociation reaction here with bromine, you remove Br minus, what's left behind has to be positively charged. And bromine is an example of an X-type ligand. That is a ligand with a negative charge. Okay, so some examples of X-type ligands that you will see in this type of chemistry. You'll see OH minus, and I'm going to show the squiggly line as the bond between as sort of indicating, I'm not sure whether, okay, so OH minus, but when it's bound to the metal, it's going to look like this. Any of the halides, okay, which we could represent like this, and this is sort of where the X-type ligand comes from. Anions, carbanions, so R minus, which would be an R group bonded to the metal. You'll see negatively charged amino groups where that R2 could be either a hydrogen or an alkyl group. Let's see, what else am I missing? Also thiols. Okay, so X-type ligands are ligands that are negatively charged when they leave. L-type ligands are ligands that are neutral when they leave. So examples of this include the phosphines, amines, water, also carbonyl oxygens, and actually also pi bonds, like the pi electrons, can coordinate a metal. Okay? Now, we are not going to worry about the orbitals that are involved in bonding for the metals. You can think about that, and there's some straightforward ways to do that. I haven't really learned them yet. Just understand that the transition metals have access to 5 different d orbitals in addition to the s and the p orbitals that are present in that row as well. So there's plenty of orbitals to go around to make new bonds. Some people like to generate hybridized orbitals for transition metals involving d, s, and p. I think that's a little bit sort of, well, just too much. You can also do the full-on completely molecular orbital theory picture, but that's also probably too much. Yeah, go ahead.
Did you say the X-type ligands were bonded to a metal?
Yes, all of these will be bonded to a metal. Over here, it's the lone pairs or the pi bond, the lone pairs on a neutral atom that are binding to the metal. Over here, it's still a lone pair that's binding to the metal, only the lone pair is on an atom that's negatively charged when it leaves. And so those electrons are here.
So like, could the water not dissociate from a hydrogen and then turn into a...
Sure. Could you deprotonate water and have it turn into OH minus? Absolutely. Yeah, convert from an L to an S-type ligand. And in fact, with the early transition metals, sometimes that's what the role of the transition metal is to do. It's to bind, you have the metal bound to water, and then that lowers the pKa of this proton, and then it's easier to remove. Okay. What else? Other questions? Okay, so the main difference between neutral and, L-type ligands and X-type ligands is L-type ligands are neutral and X-type ligands are negatively charged when they come off the metal. Okay, so now we're going to learn how to count electrons around a transition metal in an organometallic complex. So we're going to start with this Cobalt Ammonia complex, and I think it's possible. I think this one's pretty easy to make, and when I was here and took chemistry 113, which is maybe like 107, I think we made this inorganic complex. A lot of these organometallic complexes tend to be highly colorful. Cobalt complexes are usually blue. So there's a 3+ charge on the complex. Now, let's try to figure out how many electrons cobalt must have. Okay? First, we're going to note that we have 6 NH3 ligands, and that these are L-type, which means they're going to leave as neutral, right? Also, we're going to note that cobalt starts with, and this is where we're going to have to go back up, cobalt starts with what? 9 valence electrons. Okay? So, if all of the ligands are neutral and the charge is +3, how many electrons does cobalt have? Starts with 9. All of the missing electrons have to be missing from cobalt because all the ligands are neutral. Do you see that reasoning? So cobalt has 6 electrons. And we will sometimes say that it is a D6 metal in the sense that it has 6 D electrons. Notice that in the row of the periodic table where cobalt is, you might think, oh, well, we've already filled the 4s orbital, and so those aren't valence electrons anymore. But actually, the energy difference between the 4s orbital and the 3d orbitals is pretty small. So usually by the time we get to the transition metals, we're going to count those electrons as though they were valence electrons and can participate in the d orbitals. Okay, so cobalt has 6 electrons. Let's count the overall number of electrons around the metal. We have 6 L-type ligands, each with 2 electrons, and then we have 6 electrons on cobalt for a total of 18 electrons. That's an 18 electron complex. You see how we did that? 2, 4, 6, 8, 10, 12. And then there's 6 electrons on cobalt. Okay, I am seeing some frustration. What questions do you have? Should I just blow your mind that the octet rule doesn't apply anymore? Go ahead. I subtracted 3 because of the charge, yes. The reason I knew to subtract 3 from 9 here is by measuring the fact that all of the ligands are neutral, right? So if the complex has a +3 charge and all the ligands are neutral, the only other thing that could have the +3 charge is the metal. Okay, so as I look at this complex, and this is the thing that's hard relative to like formal charge on second row atoms, right? Here we were like, okay, oxygen normally comes with 6 valence electrons. It currently owns 2, 3, 4, 5. 6 minus 5 is +1, and we put a plus formal charge there. The trouble with cobalt is we are not drawing the 6 valence electrons it has. And you could, but nobody does. And that's kind of frustrating, but that's the world that we live in. One of the reasons they don't is that sometimes you've got 5 d orbitals, so it's not at all clear that if you have 6 electrons, you should have 3 lone pairs. Sometimes you have unpaired spins, and sometimes you don't. Okay. So we're not going to draw the lone pairs. Kayla, yeah.
So does the nitrogen not have a positive charge because it's not a covalent bond?
Right. So why aren't we putting pluses all over these nitrogens? And that is because, remember, formal charge was just a way of bookkeeping electrons, and we've now changed the rules. We've said that these, just by virtue of the fact that we are memorizing that nitrogen or the ammonia is an L-type ligand, then we know that the electrons in these bonds belong to nitrogen. So that's what the inorganic chemists are assuming. Go ahead.
So the reason that it's an L-type is because before it comes off, it has a positive charge. And so popping off
The reason it's an L-type ligand is if you wanted to assign formal charges and call this an actual covalent bond, yes, you could assign plus formal charges there. However, when these ligands pop off, they take these electrons with them and they pop off as neutral items or neutral atoms. One of the reasons we don't do the formal charge in the same way for these transition metal complexes is we would get somewhat ridiculous results out, right? So as an example, if I called this nitrogen positively charged, but each of these nitrogens is having a positive formal charge, I would have to come to the conclusion that the metal was 3- to get the right charge. And yet, the real place where there's positive charge in this complex is on the metal, not on the nitrogens. So we're considering these as, so sometimes people call these, for the L-type ligands, they call these dative bonds, which means that the L-type ligand is donating both electrons and continues to own both electrons. Sometimes people will draw those kinds of bonds with arrows. A lot of times they won't. Okay? So when you see an L-type ligand, you need to be thinking those electrons belong to the nitrogen. So we're changing the formal charge rule. Remember we said in formal charge, at least for these transition metal complexes, we said oxygen owns both of its lone pairs and then half of the electrons in bonds, so 5. For this transition metal complex with L-type ligands, we're saying the metal doesn't own these. These are owned by the nitrogen. Okay, other questions? That's kind of tough. That's kind of a problem. So you have to adjust that rule with the transition metals. Okay, others? Okay, let's do a few more. But notice, I guess one thing I wanted to point out is, for a transition metal, the noble gas configuration is 18 electrons. That's like a full set of electrons for the third row of the periodic table. And that's why cobalt, in the when it only has 6 electrons, that's why it can accommodate all of those 6 ligands. Okay. The other thing we want to talk about is metal oxidation state. Once you figure out, you compare the charge on the complex with the number of valence electrons that the metal has, then you know how many electrons the metal has. Then you can compare that to the valence electrons, and that will tell you the oxidation state of the metal. So this is cobalt 3+, which we can represent in a couple of different ways. Okay, let's do another one, and let's do the familiar cuprate, actually. All right. So the cuprate has a negative charge. Now, these are both, instead of L-type ligands, those are X-type ligands, meaning if they left, they're going to leave with a negative charge. Okay? So, and you can actually think of, in your mind, you can think of this as 2 negatively charged R groups, and then what should the charge on the metal be? It has to be plus in order to get the overall right charge. So the number of valence electrons copper normally has, I'm going to have to go up to our list, is 11. Okay. It currently has 11 electrons minus 1, because it's got a positive charge, equals 10 electrons. This is a D10 complex, means we will have filled all of the d orbitals. Let's figure out copper's oxidation state. If copper has 11 valence electrons and it's missing 1, that is the +1 oxidation state, or that's copper 1. And if we count the overall number of electrons, you've got 2 surrounding the metal in the complex. You've got 2 sets of lone pairs from both of those ligands, and then you have 10 from copper for a total of 14 electrons. That's a 14 electron complex. It's not completely, the valence orbitals are not completely filled. And so the key things you want out of this process are oxidation state of the metal, number of d electrons, and then total number of electrons. Yeah?
Do you have an X-type that's 2- or more than 1?
Can you have an X-type that's 2- or more than 1-? Yes. I don't have any good examples of that, but might at some point. Okay. Other questions? Yeah.
So do X-type ligands also own those electrons?
Do X-type ligands also own those electrons? Yes.
The metal never owns those.
Right. So the metal doesn't own we don't count the metal as owning those electrons. That's going to be important in a little bit when we start talking about mechanisms. Yeah.
So if there are like more than one, does that mean you have a complex with a double bond?
Can you have a complex with a double bond? Yes. We will do that in this chapter 28 when we get to olefin metathesis with ruthenium. It's really kind of cool. Yes?
Why is it more stable with just the 2R groups instead of like if you were to add like a third?
Why is it more stable with the 2R groups instead of adding a third? Yeah, you could get to higher numbers of electrons, but you're going to build up more charge on the complex. So that's probably, though you could imagine some other L ligands at this point instead of X ligands. And I don't know what that equilibrium constant would be, but there's certainly space here for them. Okay, what else? I'm sorry, I'm looking out at you guys and you're like, why are you doing this to us? You'll see. Okay, so let me show you another kind of complex that has an interesting ligand. This is a palladium complex, and the ligand is going to be the conjugate base of acetic acid. And this is an interesting molecule because it's got an L-type site there to bind the metal, and it's got an X-type site there. So we can make a complex with palladium. And again, you're going to hate this because we're giving up on our formal charge rules for the moment, and we're not drawing formal charge on any particular atom. I'm telling you that the complex here is neutral. You've got we're going to use orange for L and pink for X. All right, you've got an L-type site here, and then you've got an X-type site there, right? So if the complex is neutral, if we were to remove each of these ligands, what would the charge on palladium have to be? Each of these two ligands comes with an L-type and an X-type, which X-type is -1, right? So if you remove those acetate groups from the metal, what's the charge on palladium? 2, right? Has to be +2 so that, we can balance out the charge of the 2 acetate ligands, okay? So, and to confirm that, we can remember that palladium comes with, and I didn't memorize this, so we got to go up and look at it. Palladium comes with 10 valence electrons. It has, its current charge is +2. Therefore, palladium owns 10 - 2, or 8 electrons, so it's a D8 metal, and its oxidation state corresponds to the charge on the metal, that's +2, or palladium 2. And its overall electron count, 8 from the metal, and then 2, 4 from each ligand, 8 from ligands, overall 16 electron complex. All right, so this kind of thing is not in your textbook, so I will provide some practice problems for you so you can get good at that. But the reason we're doing this is so that you can understand some of the mechanisms that can be adopted by these transition metals. Okay? So let's return to the cuprate coupling reaction. And let's see, let me just give you, let's do this one. Okay. All right. So we already said, based on our analysis of cuprates, that this is a copper 1 oxidation state. There are 10 D electrons, and we've got R-type ligands. Okay. So one of the things that can happen with the metal is it can, and here we're going to use lone pairs on the metal. You're going to think, where did those come from? We're just pulling them out of nowhere. Well, the copper has 10 D electrons, so we can use 2 of them. And effectively what we're going to do, and it's not exactly SN2, but it's more like we take a lone pair from copper and we make a bond between copper and the carbon, and at the same time we have bromine leave and then make a new bond with copper. And let's look at how that changes our complex. All right, so I still have my 2 carbons. I added a neutral molecule to my negatively charged cuprate. So overall, the charge on this complex must still be negative. Okay. Maybe I'll show that lone pair that used to belong to the metal in blue. But now that we've done that reaction, we have an X-type ligand here and an X-type ligand there. In other words, the 2 electrons that used to belong to copper now belong to that carbon. Okay? So if we were to calculate the overall charge on this, if we were to calculate the charge on copper, we'd have to remember that we have 4 X-type ligands but we have only one negative charge on the complex, so copper has to be 3+. You see that reasoning? It's almost as though when copper attacked the carbon, it got oxidized. It lost those 2 electrons. And so this step we call oxidative addition. And we've gone from copper being copper 1 to being copper 3. Because these 2 electrons in blue that used to belong to copper now belong to carbon. And of course, these were always with bromine to begin with. If we were to count the number of d electrons copper has, copper usually starts with 11. It's missing 3. So that's now a D8 complex instead of D10. That's how you can tell it's an oxidative addition, because copper formerly lost 2 electrons. Okay? That step, oxidative addition, is something unique that metals can do. The mechanism isn't exactly SN2. We're pushing arrows, but really it's kind of like the metal inserts into this bond between the carbon and the halide. Yeah?
So it happens in one step then?
Happens in one step, same step. Okay? That's oxidative addition. Okay? Questions about that? Yeah?
Does that mean the carbon gets reduced?
Does that mean the carbon gets reduced? Yes, in the sense that it used to be a halide and now it's an anion. Right? Okay. Now, is the copper stuck forever at +3? That would be tragic, because we want a reaction to happen. So next we can do something that's called reductive elimination. In reductive elimination, I'm going to take the electrons from the phenyl group, which used to belong to copper. I'm going to move them over to make a new bond with that sp3 hybridized carbon, and then these electrons, which used to belong to the ligand, are now happily going to return to carbon. Okay? That's going to make a new bond between the phenyl group and the alkyl group. So there's our product, and in the meantime, what's left on copper? Well, you still have the Br minus and you still have the R minus. Both of these are X-type ligands. Because what came off the complex is neutral, the complex must still have a negative charge. And if you compare this to where we started, yes, this now has to be copper 1 with 10 d electrons again. So this is called a reductive elimination, because what's getting eliminated? Well, the bond between carbon and copper, and the electrons in that bond are going back onto copper. So this is the reductive elimination, is the key carbon-carbon bond forming step. And the reason it can occur is because the metal holds both of these X-type ligands close to each other, but is also can readily accept electrons. Look, it's a D8 complex. There's plenty of space for the metal to take an electron, to take a couple of electrons. And in fact, you can see that though it's not in this case, you could imagine that this process could be catalytic, because you're switching between oxidation states. Oxidative addition, reductive elimination. We would need to swap out this bromine for another R group, and then we'd be good to go again. Okay? All right. Yeah. Go ahead.
Is it ever possible for the carbon chain to bind to the bromine?
Is it possible for the carbon chain to interact and bind with the bromine? I think so, but it must be that the carbon-carbon bond is more stable. All right, thanks. We'll see you guys Wednesday.